So good afternoon, everyone. Welcome to our mini school on Haskell. Yeah. And again, we are very lucky to have both speakers. We lost one temporarily, but we found him again. And I mean, we introduced them to you earlier, so I don't have to reintroduce them to you. And we don't need to waste time with the introduction. So I hand over again to Brink and Yorick. And thank you very much, both of you, for being with us again today and sharing your Haskell wisdom with us. Yeah, thank you. So I'm not sure how you want to proceed, but the floor is all yours. Yeah.
Thank you, Francisco. So Yorick, maybe is it okay? I'll do the first half an hour and then you do the second. I don't mind doing it the other way around as well. Okay, so let's go that way.
Perfect.
Okay, so let me start by deleting what I tried out and want to do in the first half an hour. So something new I haven't shown you before is let's start by defining our own data types. So what I want to do is, so I've mentioned it before. So there's this data type called maybe. So I just want to define my own maybe type. So it's built in the Haskell standard library, standard prelude, but I think it will be of use if I show you use that as sort of quite an easy example of how to define your own data type. So it's going to be a maybe type, and we'll make that into an instance of functor, applicative, and turn it into a monad as well. And I'm using a prime just to distinguish it from the maybe version that's already implemented. So we have two constructors. The one is nothing. And so the way you should think about nothing, perhaps you have some computation. We can think of some expression type, and sometimes you divide by 0, and then from there on, the computation should fail. So you have the failure branch of your type. And then you have the other branch which sort of keeps track of the actual value. So it could be an int or a double A in this particular case. And now I'll show you what this deriving keyword is doing. And I'll derive one particular type class show. Let me just see what's going on here. There we go. Okay, missing space there. Let's try again. So just to see how it works and where this show is coming from. So say I have a variable or a function with no argument x, and I just make it just prime of 10. And now if I just type in x here in the REPL loop, I'll just see just prime 10. And the reason why that happens is I've asked Haskell or the Haskell compiler to use the default implementation or derive the default implementation of this show type class. And what show is doing is if you have an instance of the type, it will turn that into a string version. So at the moment, the way you type the actual value and the string representation looks exactly the same. And the reason why, so if you delete that deriving string and you just type X here, you'll get an error message since it wouldn't know how to turn this just prime 10 into a string representation. but let's, just as an exercise, let's derive our own implementation of show instead of using the default one. And okay, so here I'll use syntax that you haven't seen before. And so first I'll add this requirement. So you should think of show as, it's like an interface, or what we call in Haskell terminology, a type class. And in order to display something of type maybe A, I'll assume that A have a toString method. And that's what this restriction is saying here. So I assume A knows how to turn itself into a string. So it could be an int, a double, or anything else that sort of knows, have a show method. And so now I make my maybe prime A type. I turn it into an instance of this show type class. Now, if you look at show itself, you just ask info about show. So more or less all types will implement it. And the one important thing is, you see sort of at a minimum, you need this show. Well, there's another function as well, but one minimum implementation is just to implement the show. And it should simply take the type and turn it into a string representation. So let's write that function show. And so we have two cases. So if it's a nothing prime, or maybe let's return the string just to change it a bit. Let's just make that none. And now the other case with this maybe type of mine, it could also be of this type, just of A. So if it's of the type just of X, what I'll do is, so I have to return a string. So let's just return J for just and use double plus for string concatenation. And let's then call show of X. So all mine should be primed since I'm implementing something that's already there, and that's why I'm priming everything. And so recursively, this is sort of assuming this A type already knows how to turn itself into a string, and that's why I can call show on it. So let's see how this works. And so let's just reload. Let's just reload the code. And let's now make X again just prime of 10. And let's just display X again. And now we get a different string representation since this is exactly what I implemented. Okay, any questions at this stage?
Brink, did we discuss the variable names, so the lowercase and uppercase? When must things be uppercase and when must they be lowercase?
No, so yeah, so that's actually a good idea for me to mention that.
And afterwards, Yorick will have a question.
Yes, the question I was just what does the vertical line do in the first line? So in general, what you want is you want all your function names, and so variables such as functions with no arguments, they should start with a lowercase letter. And you want your types to start with the uppercase letter. And that's why I have the cap M for the maybe there and the small s. So that capital letter here, the show is what's called in Haskell as a type class. So it's like an interface, and it needs a function, which is also called show, but since it's a function, it must be lowercase. Now, this vertical bar is similar to what you find, say, in regular expressions. You can read it as or. So the maybe type, it's either nothing or it is just some value. So in this case, the variable x, so if I look at the type of x, it's a maybe type. And so in this case, since I said x is just prime of 10, the Haskell compiler figured out, well, the 10, it just said I didn't say 10 is an integer, so it figured out it must be a numeric type. So a must be numeric, and then it's a maybe prime of a where a is numeric. So let's now do something. Let's now define a type where we use recursion. Okay, Zurab, so that's just or. So this type is either this or it's of that type. So let's define a tree. And again, this a is a type variable. So the tree could have integers or strings or any other type in it. So to change this type into a concrete type, I have to sort of turn this a into sort of a concrete type. So in Java terminology, you can think of a as generics. So let's say, well, what a tree is, it's either a leaf or, so the pipe is an or it's a tree, and it's got a left subtree and a right subtree. And let's, just to make it easy, let's just let this tree derive show. Okay. And now, well, just to make it a bit concrete, so let's just make T be one of these three. So tree could be, so I don't want tree there. Let's make that node. Sorry. So a tree is, what a tree is, either it's a leaf with some value a could be an integer, string, anything. Or what it is, it's a node which contains a left subtree and a right subtree. And the deriving show part is just telling the Haskell compiler, I'm not going to implement show now. I'll leave it over to you to do the toString implementation. And what it will do is it will just print out leaf and do the string toString and a, or it will just print out node and then do recursively the toString and this part and the right subtree. So let's just make a tree. So maybe this tree contains a node, and this node contains maybe another node with a leaf with the value 10 in it, and another leaf in it with the value 20 in it. And
Brink, I think before we go further, there are two questions. But I suppose maybe Zurab's question is urgent. What is a tree? What does it do? And then there was also a question about white space, but I think maybe that will be second.
So, well, let's not do the tree2 formula, but you can think of it as you have a root node. So a tree, our trees will sort of be the reverse that compared to in nature. So there's a root node, and then from the root node will point to a left subtree and a right subtree. So essentially, this type is defining what a tree is, and you can define trees obviously in various ways. So a tree will either be, so let's make a, to make it concrete, the end. So it could be a leaf with the value 10. But maybe you want larger subtrees. So now what you do is you'll say, well, no, what the tree is it's a node, and then a left subtree with 10 and the right subtree with 20. So let me just see what's the typo.
Just going to jump in quickly. Zurab actually was asking about the a. So a is a type parameter. So it's a parameterized type. So it tells you what goes into the tree.
Yeah, exactly. So yeah, that's also important. So with this tree of mine, at the moment it's a type parameter, and to make it concrete, you have to say, well, A is an int, or it's a string, or whatever. So and something you can do, you can ask the Haskell compiler to tell you what is the kind of tree. Oh, maybe I didn't save it. Let's see. So if we ask for the kind of tree, okay, I thought it's, maybe I'm wrong here. Okay, it doesn't want to do that. Let me see the kind of, maybe. Oh, okay. So let me see. I'm not exactly sure why I didn't do that. So for example, with this maybe type, so my maybe prime is sort of the same as the built-in maybe. So if I ask for the kind, it's saying the kind is star to star. And the way you should read it with this maybe type, just like the tree type, you have to provide one additional type, concrete type, to make the actual type into something concrete. So that's just a type variable. People in Java would call it generics, or other languages. Okay, let me just see. Well, maybe I didn't.
The second question, I think, was about the white space and layout, if it is meaningful.
Yeah, so that's something I also should have mentioned. So similar to Python, white space is important, and so sometimes if you don't do the indentation the way the Haskell compiler wants it, you'll get an error message. So there's error messages that you get just because you don't follow the layout rules of Haskell. So white space is important. So that's why, well, you could use it, but we don't use say semicolons and braces and things like that. We just use white space, and so white space do play a role, and you could get error messages if you don't do it correctly. So yeah, so let me see if I now ask for the kind of tree. Will it? Yeah. Okay, I just didn't save and reload. So yeah, again, the kind of tree, it's saying star to star. So the way you should read it, you have to provide an additional type. So something could be, the A could be an int, for example. So tree of int is then a concrete type. So if you provide one more type, you'll get a concrete type. And in Haskell, they call that the kind of tree. So one type is missing. Yeah, so sort of, yeah, the so with via recursion, this is obviously an infinite type. So I would say a good exercise. See, so I've shown you now, yeah, a tree, but it would be good if you, what we do here with trees and the maybe type, do it for lists. So implement your own version of lists. So, right, so we've looked at lists, which is, well, it's more streams. It's not like arrays really. We've worked quite a bit with lists in the previous two lectures. So see if you can do, and right, we sort of said that's just syntactic sugar for 1 cons, 2 cons, 3 cons, the empty list. So see if you can implement your own list data type. That's maybe a good exercise for you to do. So now what I want to do with with my maybe type here, maybe type here at the top, let's and so hopefully you guys with familiar with category theory, you comfortable with functors. So what we want to do is, so again, functor is like an interface or a type class, and it makes certain guarantees. So at a minimum, we have to implement an F map. So I want to make my maybe type into a functor by implementing this type clause, and I'll implement fmap. Now, again, notice here I've mentioned this idea of the kind. So the way you should read it, you can do functor for something where you need to, its kind must be star to star. So it needs one type variable. So we can just do functors for things that need one type variable, like lists or maybe or tree. So we can, all of those, we can make them an instance of the functor type clause. So just to sort of give you a sample of, let's just use the fact that list is a functor. So let's do fmap. And let's fmap. So recall plus plus is just concat. So what I want to do is, this is a function that concatenates to the right of a string, the exclamation mark. And let's now apply it to a list of strings, say hello. There. So I'm fmapping this function over this list of strings. And then it just adds an exclamation to the right-hand side. We can do this since lists implement the functor type clause. Now, what I want to do is I want to make this maybe type of mine also an instance of the functor type clause. Okay, so let's try that. So essentially, we have to implement this fmap thing. And so what's initially slightly confusing here, this f here isn't, that's really your type. That's not the function that will take, that fmap will take. So the f is the maybe type or the list or the tree. So let's make, so let's go instance. So that's the syntax to make a type an instance of a type clause. So instance functor. I'm not sure if I need parentheses. No, I don't. Maybe where. So we now I'll specify this fmap function. So we'll go fmap of a function, and if we apply it to nothing, and since I'm priming it, since there's already a maybe without, where the one side is nothing, so that's why I'm priming it. So if I map over something which is nothing, I'll just return nothing. And now let's fmap, here's the function, and let's fmap over just of x. Then what we should get is just of f of x. Let's see why it's unhappy here. Oh, okay, again, somehow I forgot the primes, since it's not the usual maybe, it's my own maybe. Yeah, no, that's happy. And so let's now use this. So let's just reload it. And let's now fmap. And let's first do an easy example, then a difficult example. Let's just fmap times 2 over, well, I guess I don't need, just prime of 10. So just like we mapped over list, since the maybe type is now a functor, I can map over it. Okay. except it's unhappy here. Aha, it, yeah. It has to do with presidents and all kinds of things like that. So if I if map the times 2 function over just prime of 10, that turns into just of 20. And the reason why we see J20, remember, we implemented our own show method up here and specified it in that way. Now, last thing from my side, let's do something a bit more fun. Let's put there $2. And here in the maybe type, let's do this. And let's see what happens and if anyone can, and then I'll look at the chats as well. So essentially what is happening here is inside my maybe type with the just, I'm putting inside it a function, which is times 10. And now the function application, the function that I'm applying is essentially, it's the function where I give the argument of 2 to this function. So what this dollar is doing, dollar is, I've mentioned it once or twice, dollar is actually a function where the first argument is a function and the second argument is the argument of the function. So dollar is a function. And so the first parameter, here it is. There's the second parameter, it's the 2. So essentially I'm seeing here function, applying the value 2, that's in fact the function. And I'm applying it to the function times 2. And that's why I get just of 20. Okay, let me see the... Yes, so I should... it is similar to Python, yes and no, but I have to admit my knowledge of the white space rule in Python, I haven't studied it carefully. It's more a matter of I've seen when the compiler complains, and maybe for next time I should read up a little bit more carefully on it and sort of in general with I guess we can.
I think
if we just do some.
Sorry, it's similar but not the same.
Not the equal, yeah, that's a good. So I suppose if I do this, it might complain. Let's see, is it happy? Oh, it still compiles. I thought it might complain there. I know if I get to the do notation there, it's quite finicky about the layout and so on. So yeah, so it's similar, not the same, but I let the compiler complain, and I must admit I don't know the details there. So what I'll do next time, so if I just show you the maybe type, you see it's a monad. So I'll show you how to make it applicative. I'll show you how to turn it into a monad. I'll show you how to make my tree over here, how to make it foldable. So if you want to try some of those things, and maybe if you want to try some of these things on the list type, so make your own list type. Okay, so I'll stop sharing the screen.
Maybe we should just ask very quickly if there's any questions. I don't know.
Yeah, that's a good idea.
So I was actually wondering, so you've got, it seems that the functor can always only be implemented in one way. Is that right?
So if you say sort of,
I mean, there can only be one instance of functor maybe.
Yeah. So there's just one way to turn maybe into a functor. So often what happens is you want to in more than one way to sort of implement functor or some other type class. And I'll also show that to you next time. And then what you do is you put your type inside a wrapper type. So a typical example is something, say we'll look at integers, and I want to turn integers into a monoid. So I have identity and I have one associative binary operator. So then it's the question, do I want to use the plus or the times to turn my ints into a monoid? And then what you have to do is you have to put your ints in a wrapper. And so you have one wrapper type that turns where you use the plus for the binary operator. And you have another wrapper type where you use the times.
It seems we might have lost some in the audience. I don't know if we can see how many are lost, but Zurab is I think, not following everything that we've done.
And Zurab can just unmute himself and ask, you know,
Zurab, go ahead. Okay, go ahead.
Well, thank you. I don't want to distract the flow of the lecture.
No, so it's important. It's more important. I think there's more value in making sure almost everyone follows these basics than getting to super advanced stuff. I would rather want people ask questions and we talk about the basic elements.
Okay, then if we go back to the beginning, the first line,
where I defined maybe.
Yes. So can you explain what is happening on that line intuitively? What is being defined there?
So I'm defining here a type. So maybe I should sort of contrast it to when we looked at lists. So I wanted to define something like you would have lists, and a list could have integers, or a list could have characters in them, or any type you want. So there's no restriction on the type. So similar to lists, I wanted to define this maybe type, and the reason why I primed it is there's already this maybe type. So I'm essentially just implementing this maybe type, my own version of it, since I thought that would be instructive. So now I'm saying if you want to make, so this A could be, it could be an integer or a double.
Sorry to interrupt. So this is where I don't understand. So you're defining a type, but now what's the purpose of A?
So it's so it's almost like when you have, say, a function that takes a single argument and it returns something. So this type is generic. To make it concrete, you have to give it one of the types you already have.
So is this type itself a function?
So what is a function is the nothing prime and the just prime. Since what they do, so, and in fact, we can check that. We can say, well, what is the type of nothing prime? And it's saying, well, what it's doing is it's something that gives me something back, which is of type maybe prime A.
We didn't define nothing prime before, did we?
No, it's defined. Here you can see it doesn't take any arguments. It just returns something. And just like that, if I ask for the type of just prime, it's just saying, you give me an A, and I'll give you something back of type maybe prime A. So this is another languages people talk about constructors. So this is how you construct the things of the type. And you have two ways of constructing a value. Either you use this constructor function or you use this constructor function. And I think sort of the one part you find difficult is this fact that, let me say something. Let me
I understand it much better now. So we kind of read from right to left in some sense. But then what is the point of A on the left side of the equality? So now I understand now a bit better what's happening on the right side of the equality. What does A do on the left side of the equality?
It's just saying it doesn't matter what, you have to give one more type A, and it doesn't matter what that type is. So let me see if I can explain it. So I have a Y here, and I said it's just the int 5, and I specified that as an int so that it wouldn't just be a numeric type. And now I can say, well, let's make X equal to just prime of Y. And now I can ask, what is the type of X? And it will say, well, it's maybe prime of int. So it took my definition and it realized for everything to type check, X must be that A must be of type int. So yeah, I said it's almost like a function, so that needs an argument. This is sort of a type variable, and to make this type into a concrete type, you have to give one more type. So in this case, I gave one more type, which was an int, and now this maybe prime of int, that's a concrete type. Since it's too much hassle, or it's just not sensible to say, well, now I have to say I want to use this maybe type. Now I have to define a maybe int, I have to define a maybe string, a maybe double, whatever. So I just want to extract the pattern and say, I don't care what the additional type base type is. This is the type I want to construct.
Thank you. And what is the intuitive understanding of maybe prime int? So why would we want to have this nested types?
Yeah, okay. So that's also, I'll show next time the example, but so imagine I make a type view expression, and let's make it concrete, this expression of int. And what an expression is, it's either an integer value or it's the division of one expression by another expression. Okay, I don't need that there. So what an expression is, it's either an integer value, so value of integer, or it's the division of two expressions. So again, yeah, I just made a type. And now imagine you want to define an eval function, and what it should do is it should take an expression and it should give back the integer value. But now the problem is, well, potentially you could divide by 0, but perhaps when you evaluate the right-hand expression, so for example, val 0 would be one example. If you evaluate the right-hand expression, it's 0. So when you divide, and then you're going to divide by 0. So what you rather want to do, either there's an error or you get an integer value. So a nicer way or a design pattern would be to say, well, what a val is going to do is it takes an expression and turns it into a maybe int. And so if it's possible to divide, it's going to put the value inside the just. But if there's an error, the whole calculation will just say nothing is the answer. So yeah, so that's typically where you use the maybe type. You have two flows in when you write your code. You have the normal flow where everything goes right, and you have the flow where some error occurred. And instead of throwing exceptions and all kinds of crazy stuff, you just make a new type that keeps track of whether you've had an error or whether the value should just be propagated.
And how does Haskell know that nothing is the one for the error?
So when we implement this evaluate, we'll make it clear, number one, and number two, if you also, okay, now I'm also getting ahead of me, we'll have this bind operator from monoids. if you look at how the bind is implemented for the maybe type, you can see that from that you can deduce that, or the compiler can deduce that the nothing is really the error. And just like for example, now I've shown you where the nothing is error and just as a true computation, there's also a type, built-in type, either A or B, and that is left A or right B, which is sort of more on steroids version of, so I guess I need to say data, that's why it's complaining. So in this case, what you do is your right part will be the true computation, but you can imagine with your left part, you have both the error, but perhaps you also want a string message that say, well, this was the error. You want some logging information. So there's sort of more advanced versions or versions of this maybe type where you can also sort of log what was the error that occurred. What was it, division by 0, or was it some syntax error? What was the error? So there's sort of more involved versions of the maybe type, and that's the reason why you use it. And I'll show you once we have this next time. Once we have this maybe type and then into a monad, you write some beautiful code, and the magic is just hidden about behind this bind operator that you have, since the maybe type is a monad. Yeah, I should say, yeah, hopefully that answered. I should say I'm always surprised with my fourth year students. Many of them struggled with mathematics, but then suddenly if I show them monads and Haskell, pretty soon they sort of better at manipulating it than I am. So that's always the thing that surprises me, how much abstraction they can handle in code, but how little they could handle, say, in pure mathematics. That's always weird. I don't understand why that happens. Yorick, sorry, I've stolen too much of your time, but
No,
let me stop sharing, and maybe next time you should begin, then you steal my time. So yeah. I'm going to hand over to you.
Sure. Okay, I'll take a step back and hopefully go back to some things which are a bit simpler. And we take requests. So if there's anything that you think this would be nice to see in Haskell, maybe in Kumo Space, you can just afterwards let us know. And if it's within our abilities or within my ability, I'll have a go at implementing it. So I've picked a couple of examples. We'll see how many we get through. And just to get some idea, if you watch the video that Brink linked to last time, you will notice that there's not a very good definition maybe of what functional programming is, but maybe just to get the idea of what the spirit of functional programming is. And so that's mostly about lots of functions doing very simple, understandable things and composing to give you your end program. But that means that certain things you should try to think of in maybe slightly different ways. So the first one, I'm going to look at maybe 2 examples, and from there we'll see. The first one is the Sieve of Eratosthenes, which is to say that to find prime numbers, what you do is you create a list from 2 up to infinity, and you start crossing off the things that are not prime. So you have the first number is 2, and then you cross off all multiples of 2 in your list. And then what's left over, the second number will be 3, and you cross over what's left over from the list from that point on. So what we can do, let's see if we can define it. Firstly, let's look at, we do have infinite lists, so I'm going to do something probably that's going to cause problems. So I can have the list from 2 to infinity, and it will not stop. So I've interrupted it there. We want to calculate the sieve of a list. Well, if it's an empty list, then there's nothing to do, so it's just empty. If we want to apply the sieve to some x followed by more numbers, then it is the x that we have, so the first element, so if it's starting with 2, 3, 4, so on, then 2 should be considered prime, and then we'll cross off everything which is after that. So we'll take from the rest everything from the x's, and I've got a cheat sheet, so, and this is where division with x, so we're crossing off all of the entries which are divisible by x. And we leave those which are not divisible by x. Okay, so from here, we can take the prime numbers to be Sieve applied to the infinite list. Okay, so let's see if that loads. So let's save first. If I did it correctly. Of course, I didn't put in
I think, yeah, your y, yeah, and then the conditions,
yeah.
exactly, yeah.
Okay, so thanks. And then I'm also too many dots. Okay, so if we now look at the primes, of course, it's going to be an infinite list. That won't be so useful, but maybe we can take the first 5 primes and then we can see it, or we can take the 100th prime from that list. If I did it, oops, take is wrong, primes, 100th prime from the list, and we can obtain each of the prime numbers. Why this is interesting is I'm going to use this idea for another example, but this is what is called streams. You create infinite lists, and by lazy evaluation, you don't need to know what the rest of the list is. And so you can construct things lazily and only use them as you need them. So we're going to use this to hopefully give a nice example of a numerical method. Of course, this kind of thing you can do in other languages too. You can do it just by writing your functions in a recursive way, using producers and consumers and those kind of models. It's not that it's new, but it's certainly quite elegant to type in this way. So what we're going to do for the second example is look at a numerical method. So I assume most people here will know it, but if you don't, I'll try to explain it quickly, which is that if we want to find the root of a function f, so the value x at which f is 0, assuming it has 1, it's given, well, we can approximate it firstly by the first order expansion. F of x plus h is approximately f of x plus h df dx. So to find a root given a point x, and we want f of x plus h to be 0, so we take that equal to 0, we find that we can solve for h, and it's just minus f of x divided by df dx, so the derivative. And this gives us a way to have successive approximations. So if I'm not close to the root, maybe I've got an h that will get me closer, and I calculate it this way. We won't go into the convergence properties. We're just going to assume that it will converge. So I've picked an example here. I've got a function p of x, which is just polynomial. And I would like to try to find a root here. Obviously, the roots are 2 and 3. And I'd like to see how to maybe calculate that. So a naive approach would be what I'll call Newton 1, given a function f, its derivative, and value x. And what I want to do is I want to get close enough. So some epsilon that tells me whether I'm close enough, equal to. So what we would like to say is maybe what we're going to do is not write it in this looping style. So this is a traditional loop. While the absolute value of f is too large, so we're not close enough to 0, try to find a better approximation and keep doing that until it converges. So how would we do that? Well, we know we can stop if the absolute value of f of x is less than epsilon, then x. Otherwise, what should we do? So what we want to do is this looping structure, and I think last time we spoke about accumulators. So what I will do is accumulate the answer in x. So I will take Newton 1 again, same function, and its derivative. And I will use x1. So that's a new value, also to accuracy apps. And then this is where the white space is sort of flexible. So where x1 is now this formula. So it's x minus f applied to x divided by the derivative. That's right? I think so. Okay. So that would be my naive first implementation. Let's reload and let's see if this works. Newton 1 applied to P and dP. And we'll start, should we just start at 0 and some approximation. And we see we find something close to 2. So I don't know if anyone's thought of doing it this way so far. This is almost an imperative way of doing things, except that we're carrying the answer in X. Instead of looping, we just keep looping inside the accumulator, inside the answer.
Yeah, Yorick, perhaps also something basic with your code I can just point out to everyone. You also see the functional nature in your if then else. So you always need an else branch since it must be a function.
That's true.
You need to return something if the condition is true, but since it's a function, you also need if it's not true. So essentially, the if then else, it's a function, and that's why you always need the else clause.
So what you're saying is you cannot say if this condition is true, do something, but otherwise I don't care.
Yeah, exactly.
You have to actually care.
Yeah, exactly.
It's like a case statement in your function. Yeah. All right. So I would say maybe this is not quite in a functional style. In one way, I find that I'm very much mixing up what I'm trying to do. One is the calculation, which I could conceivably do forever. And the only thing that I want to do is say when I should stop. So maybe a first example of what you can do, just show you first a function that's in the standard prelude. If I say drop while even 2, 4, 6, 9, 10, it will take off all the even numbers, and as soon as it encounters something which is odd, it will stop. So I can make a list and drop everything in the beginning that doesn't satisfy some condition, and then look at what remains. So what we're going to do is do something similar. So again, f, df, x, and epsilon. What I want to do is take, how we're going to do it for this one. Maybe I should show you head as well, in case we haven't seen it. Head of 1, 2, 3 is just going to be 1, so the first element. And so what we're going to do is say, take the head of drop while. And so we want to check if we want to continue on. So let's call it continue. And then what we're going to do is apply this to the iterations. So let's do where on the next line, where iterations. Okay, so what do we want to do? I'll make this a function. I'll create all the iterations from x. And what it does is it takes x and, well, we'll keep it. And then we will also, what are we going to do? We'll just immediately apply the iteration. So take the formula. So that would be my next iteration. And then concatenate this with the same thing again. So let's x1, and then I'll take x1 to be this statement. Right, and so I also need to know what continue means. So continue is, continue of x is when the absolute value of f of x is less than epsilon. So hopefully we've got that right. So we've got an infinite stream of iterations in this same, using the same formula. We start with x, and we make x1, which is this formula, and then from there we generate the next step and the next step up to infinity. So hopefully this is correct. And let's try Newton 2. And if we do something strange.
My guess would be with the continue, isn't it larger than instead of less than?
Yes. I'm sorry, yes. We must continue while it's not.
Yeah.
Thank you. Yeah. Let's try again. And now I've also messed up the stopping condition, haven't I? If x continue, and I'll have to go to my cheat sheet again. Continue is that one. And use the right formula. And this is why live programming is never a great idea. So let's see. Line 25. So Keegan, are those the parentheses? Let's just see. Yeah. I must have some small typo because it's not converging. Let's see. So iterations of x is correct. The only other option is I chose the wrong, so that should be fine. So I'm going to have to appeal for help from Keegan. Also infinite loop. Okay, so the drop while should be fine. Continue. Should be okay. So the only thing in my cheat, I didn't do the first one the same, but let's just check. That shouldn't be a mistake. Let's see. Alternatively, the GHC that I tested on is different. Brink, do you see anything else? X1.
Seems I'm not 100% awake yet. I should have seen it now by now, but I haven't yet.
It's the same as what I have in the printout, pretty much. So normally it's when I switch these two around. 0, so that's fine. Let's just. Of course. The x1 is from here. It should be where x1 is this one computed from this x. It would have been more obvious if I changed the variable names. I was picking up the wrong x.
Yeah.
So let's make it clear. Oops. There we go, that's fixed. Okay. And of course, what I'm doing here is reinventing the wheel. So the one last thing I will note with this calculation. There is a third version. But this iterations of x that I've written is actually already, there is such a command, which is called iterate in Haskell. And so you give it a function, so I'm going to call it the Newton-Raphson iteration. And all you have is Newton-Raphson x0. We don't need this anymore. It gives us the next value from x0. So let's see. And that gives us the same answer. So the reason why I would say probably this is a little bit more functional is I've separated out everything into sort of the role that it must play in this calculation, which is what is the stopping condition, what is the iteration, and now, of course, we could easily adjust this for modified methods from this. We could do it here also, but it's very clear. So the style, I would suggest, is more functional. And then, so we're actually over time now. I was going to look at Gauss elimination, but maybe we should look at that next time. Are there any questions besides spelling variable names in a useful way?
Hi, sorry, can I ask a question?
Yes.
I know it's going to be a silly question, but when you say iterations x0 equals, after that, what does this x0 do?
This x0 on the right-hand side?
Yes.
So this is concatenation, which means if I have a list, say 2 and 3, and I put colon in between and put a 1 on the front, it just puts it on the front.
Thanks.
Good.
And in functional style, you can also explain it as a function.
Yes.
which takes a value of type A and a list of A's and gives you a new list of A's. So yes, it's a function taking 2 arguments and giving a list back.
Very good, yes.
But the arguments of that function are on either side of the function, because the column is the function here, right?
Yeah, so it's infix. You use it in infix style.
So colon, yeah, okay. Colon takes a value and a list and creates a new list. And well, if I did it just directly, what happens? I haven't tried this. So the colon isn't something that stands on its own, it stands between things.
So in my limited understanding, if you want the type of an infix function, you have to put parentheses around it.
You have to section it, yes.
Section it, exactly. Same with plus and so on.
And you can also, of course, section it on the other side. So the operation that adds something to the front of a particular list.
Yeah. Well, I guess now you've supplied one of the arguments.
That's right. Yeah. So
right, and
it's just left or right currying, right? So
yeah, exactly. Yes.
On whichever side you like. Yeah. Okay, I don't know if there's any more questions. I don't think we'll have time to do anything else. But please, if you want to request anything in Kuma Space afterwards, we'd be happy to look into it.
Yeah, Yorick and Brink, thank you so much again for guiding us through understanding slowly, every week a little bit better, the intricacies of Haskell. It's really fascinating to see how this different programming paradigm works. Yeah, it's really very nice. Thank you so much. It's really very interesting. As you said, Yorick, it seems we don't have any further questions at the moment. But again, like always, everybody is invited to join us for a quick informal chat in Kumo Space, and I just reshared the link in the chat. So if you look on the chat, you can just click on the link, and it should bring you automatically there, where you'll have again the opportunity to chat with Yorick and Brink and with others, and maybe express some of your wishes for next week. Yeah. So I think it's just my pleasant duty to thank you again, Yorick and Brink, for another exciting lecture. And I'm looking forward to see everybody next week here for the continuation, and maybe afterwards in Kumo Space for a chat and a cup of tea. Yeah. Thank you. Thank you very much. Thank you.
Thanks very much.
Thank you.
Have a good afternoon. Thank you very much.